Okay, I'm going to talk about the trip operon today, which essentially in prokaryotes makes tryptophan. And the way it does this, it's an anabolic process. It makes these different proteins. If our RNA polymerase comes down here and transcribes to these 5 sequences, it'll translate into these 5 proteins. These proteins come together to make a protein structure that will make tryptophan. If we need tryptophan, if there's low levels, then it will transcribe these sections. If we don't need them, we're going to stop it back here so it doesn't have to transcribe these and use the energy up, and we can save energy. And there's 2 different ways it does this. The first is with what we call the trip repressor right here. And the trip repressor is just kind of hanging out. Our RNA polymerase 2 is coming down, it's transcribing through here, transcribes, and then we make some tryptophan. And now right in the cell we have a lot of tryptophan, right? This is tryptophan. And tryptophan will come and it'll bind with the repressor. And when it binds with the repressor, the repressor is able to bind here at what we call the operator. When the repressor binds the operator, because there's a lot of tryptophan, the RNA polymerase comes down and tries to get past it, but it can't. It's stopped by the repressor, meaning it can't get to these 5 proteins, it can't translate it. The other way is what we call attenuation. And attenuation is really cool because it's like a dimmer on a light switch. Essentially, if we have a lot of tryptophan in the cell, like this, RNA polymerase is going to come down here to what we call the leader sequence. And as it's transcribing the leader sequence here, it's going to transcribe it into this mRNA, and our ribosome is going to start translating this mRNA. Right? And in this mRNA strand, there's 4 sections, 1, 2, 3, 4. 1 and 2 will bind together to make a hairpin, and 3 and 4 will bind together to make a hairpin. And this is followed by a poly-U tail. And we know that a hairpin followed by a poly-U tail, that'll be a terminator site. So if there is a lot of tryptophan in the cell, there's these 2 tryptophan codons right here. As RNA polymerase is transcribing and the ribosome is translating, if it gets to here, there's a lot of tryptophan, the ribosome will just put the tryptophan in really quick. It'll continue on down the line. This will continue translating, and we'll get 1 and 2 binding together, which means later on, 3 and 4 will bind together, rip the poly-U tail out, and transcription will stop before it gets to these sections. If, however, there is low tryptophan, then as we're transcribing, we're going, we get to the leader sequence, mRNA is being made. The ribosome gets through here, and it gets to these sequences. There's not a lot of tryptophan, so it stalls. Can't put tryptophan in there, it stops, which makes it so 1 and 2 can't bind together. This keeps going, transcribing, 2 and 3 bind together, and this does not terminate. It doesn't pull the poly-U tail out, it just continues on and translates these. For mutation, let's just say that these 2 spots right here code for lysine. Let's say this is lysine, and we have a lot of lysine or little lysine. This will depend on the amount of lysine, and if there's a lot of lysine, then it won't make tryptophan. If there's little lysine, it will make more tryptophan, even if it doesn't need tryptophan. Hope that makes sense. This is the trip operon.